The purpose of this segment is to introduce you to the concept of isomers. That is, two molecules that have the same formula, meaning the same number and type of atoms, such as C3H6, but have some sort of difference in the structure of the molecule. We're going to, by the end of this segment, determine what terms we can use to describe the relationship between two molecules that are related to one another and that they have the same number and type of atoms, but they have some structural difference. We'll walk through the terminology here, and then in the following segments, what we're going to do is look more in depth at several of these different types of isomers and additional terminology that goes along with describing those. So let's go ahead and get started with discussing the different relationships between molecules. And there is a handout that goes along with this particular segment that you can access. So when we're talking about isomers, what we're referring to always is two molecules that have the same formula but have some sort of difference in their structure. And we're going to go through this flowchart here to identify the relationship between any two isomers. There are a number of different specific terms that we use to describe what type of isomer a couple of molecules are related as. So once you've identified that two molecules share the same formula, they have to either be completely identical molecules or they have to be related to one another as isomers. Starting in, on the left here in our flowchart are the constitutional isomers. Constitutional isomers is a term that came up in an earlier segment. And so we're not going to spend a lot of time on that here, but what we're referring to when we talk about constitutional isomers are two molecules that have the same molecular formula, such as C3H8O, but they have a different way that the atoms are connected. In other words, in going from one constitutional isomer to another, one or more of the atoms in the molecule has actually moved to a different location. So for example, if we look at the two alkene molecules here as an example, you take a look at the double bond location has changed from being between carbons 1 and 2 of the chain and being here between carbons 2 and 3 of the chain. As a result of moving that double bond, what you would see is that the atoms have also changed positions. So in this molecule, we have a CH2 group at the end. In this molecule, we have a CH3 group at the end. So we've definitely moved at least one hydrogen in going from the structure on the left to the structure on the right. So that means that those two molecules are related to one another as so-called constitutional isomers. One way to recognize constitutional isomers is that if you can specify a different IUPAC name for the two compounds, then the two compounds must be constitutional isomers. The other type of isomer, referred to as a stereoisomer, those molecules will always have the same IUPAC name with the exception of terms that describe stereochemistry, such as the term cis and trans is a descriptor of stereochemistry. So for example, if we were looking at, as constitutional isomers, the molecule on the left, which looks like a giant X at the moment, but remember those ends in the line and intersections in the line represent our carbon atoms there. So if we were comparing these two structures, we would establish that both of them have the same molecular formula, that is C5. They each have 5 carbons, and they each have a total of 12 hydrogen atoms. So they're both C5H12, so therefore we identify they have to be isomers of some sort. And then when we look at the structures of them, if we come up with the longest carbon chain to name each of these, we'd find that this one has a 3-carbon chain with 2 methyl groups at carbon 2, so it'd be 2,2-dimethylpropane. The structure on the right, on the other hand, finding the longest carbon chain, would certainly have a different IUPAC name. Its IUPAC name would be 2-methylbutane. So these two structures that we've shown here are certainly related as constitutional isomers. Constitutional isomers, again, means that you have changed the location of the atoms in going from one molecule to another molecule. So constitutional isomers are the result of atoms actually moving from one spot in the molecule to another. So the atoms have relocated. Stereoisomers, on the other hand, are going to be our second bucket that we can dump isomers into. So when we look at two molecules and we're establishing their relationship, they'll either be categorized as constitutional isomers, which means they have a different connectivity between the atoms, or they'll be classified as stereoisomers. Stereoisomers have the exact same connections between the atoms, meaning they would have the same IUPAC name, they have the same atoms in the same places along the chain, but they're going to differ in the three-dimensional shape of the molecule. So they're going to differ in how those atoms are oriented in three-dimensional space. So which atoms are connected together remains the same from one stereoisomer to another, but they're going to differ in how those point, whether they're pointed forward or backwards or left or right, how they're oriented in 3 dimensions. So going onward down the list of features of stereoisomer, this is what we're going to dig into really deeply in this particular chapter, is this concept of stereoisomers. So stereoisomers we can put into 2 categories. One of those 2 categories we've looked at previously, and that's the conformational isomers. So those are going to be stereoisomers that we can interconvert, meaning we can transform between one and the other just by rotating around single bonds. And it's typically those carbon-carbon single bonds that we rotate around to interconvert between conformational isomers. So examples of conformational isomers would be if we had 2 cyclohexane derivatives that are related as ring-flipped versions of one another, we would describe those as being conformational isomers. So examples of conformational isomers include ring flips of cyclohexane derivatives that we covered a couple of chapters ago. Another example of conformational isomers would be when we rotate around the carbon-carbon bonds of an alkane to give different Newman projections that relate those different conformations. That would be an example of 2 molecules shown as a conformational isomer. So we can also put alkane conformers here, which that was commonly shown using a Newman projection. So those are going to be your conformational isomers, and since we've already discussed those a couple of chapters ago, we're not going to go into a lot of detail here. We're just trying to establish the way to systematically use this flowchart to go about identifying the relationship between different molecules. So conformational isomers are going to be things like ring flips of cyclohexane derivatives and rotating around carbon-carbon single bonds of linear alkane molecules. All right, so our other type of stereoisomer is going to be the configurational isomer. And yes, there's a lot of terms here that have the letter C in them and start with CON, conformational, configurational, constitutional. Make sure that you're clear on what each of these terms mean, since they do sound pretty similar if you're not really up and sharp on this. So configurational isomers are going to be stereoisomers that we cannot interconvert between by just rotating around carbon-carbon single bonds. So all stereoisomers are going to fit into one of these 2 categories, either configurational, which means we can rotate around carbon-carbon bonds all day, and we still won't be able to make the 2 molecules totally identical in terms of how the atoms are oriented in 3-dimensional space, or conformational isomers there on the right, which are isomers where when we rotate around carbon-carbon single bonds, we can ultimately create 2 molecules that are totally identical to one another. We're going to focus now on the types of configurational isomers, which this is going to comprise the majority of our discussion for this particular chapter, is looking at the 2 types of configurational isomers. Those 2 types of configurational isomers are referred to as diastereomers and enantiomers. So all configurational isomers will fit into one of these 2 categories, either diastereomers or enantiomers. So once you establish that no matter how much you rotate around some carbon-carbon single bonds of the molecule, you can't make the 2 structures that you're comparing totally identical to one another, that's the point at which you then say to yourself, well, the 2 molecules have to be related to one another as either diastereomers or as enantiomers, and your job is to determine which of those 2 it is. So we're going to start with enantiomers and give just a bit of an overview here, and then we're going to have an entire unit on enantiomers as we dig into the chapter further. So first off, enantiomers are going to be stereoisomers that are related to one another's non-superimposable mirror images. So just like your left and right hand are mirror images of one another, yet they're not superimposable, the same is going to be true with stereoisomers. So if we take a look at the structures here in the lower left-hand corner, those 2 molecules are related as mirror images of one another, because you can see as you look at these structures that much like your thumbs, the 2 chlorine atoms are oriented toward one another. They're both pointed forward here as wedges that I've highlighted in red there. The hydrogens are dashes. That means they're pointed away from you, and see how they're oriented toward one another as dashes facing each other, much like your hands are mirror images. And then straight up is your hydroxy group on both of them, and straight to the left versus straight to the right, meaning in the plane of the page, you have your bromine atoms. So these two molecules are related to one of those enantiomers. They are mirror images of one another. And more specifically and essentially, for them to be described as enantiomers, they have to be non-superimposable mirror images. And when we say they're non-superimposable mirror images, what that means is that no matter how you reorient the molecule, no matter how you rotate it around, you're never going to be able to make all the atoms totally superimpose on one another. So we describe them as non-superimposable mirror images of each other. If you look at two molecules and they have this relationship where it's an object and it's mirror image, and they're not superimposable, we'll describe those molecules as being enantiomers of one another. So the two structures up here, we can also describe as enantiomers, as mirror images. And you may be looking at those two structures and saying to yourself, I don't really see how those are mirror images of one another exactly. Well, the way that we can better see that they're mirror images of one another is by rotating or flipping one of the two molecules. Will allow us to illustrate that they are mirror images. So if we take the structure that we have in the upper left there and we just flip it over, it will still have our total of 5 carbons in the chain. But once we roll it over on its belly or roll it over on its back, whatever you want to say, the OH group is going to come over to the left, and rather than pointing toward you, it's going to point away from you. And you can illustrate this with a molecular model. If you have a molecular modeling kit, you can illustrate how if you flip the molecule over, the groups that were facing forward initially are then going to be facing reverse and on the opposite side. So left, on the left side of the molecule here rather than toward the right side of the molecule. Our chlorine atom, on the other hand, once we flip the molecule over, is going to be over here, and it's going to be facing forward rather than reverse. So a wedge rather than a dash, in other words. So if we compare now the two structures that we have here, that is, we've redrawn the structure from the right down below in black, and we compare that to the structure up top. Now, hopefully it is easier to see how these two structures are related as non-superimposable mirror images of one another, making them classified as these so-called enantiomers. Because if we put these side by side, we would see that they are mirror images of one another. So when we're talking about enantiomers, non-superimposable mirror images, in order for a molecule to have an enantiomer, in order for it to be non-superimposable on its mirror image, it has to have at least one so-called chiral center. A chiral center, by definition, is a carbon atom that has 4 different groups bonded to it. So it's a carbon with 4 different groups. And anytime a molecule has at least one chiral carbon, that molecule will have an enantiomer, a non-superimposable mirror image. So recognition of chiral centers is going to be absolutely key to recognizing enantiomers. So carbon with 4 different groups bonded to it is defined as a chiral center. Any molecule with 1 or more chiral center will definitely have an enantiomer, a mirror image. So if we take a look at the structures that we were using as our examples down below, and we look for chiral centers in those molecules, we're looking for carbons that have 4 different groups bonded to them. If we take a look at our structure right here, I'm going to put a star on the chiral center. So my star indicates the chiral carbons, or the chiral centers, the carbons that have 4 different groups bonded to them. So I put a star there. I'm going to put a star right here on that structure because that's another carbon that has 4 groups bonded to it. So the fact that we have a chiral center in that molecule indicates there has to be an enantiomer that exists for it, a non-superimposable mirror image. We come on up to our structures that have the hydroxy group and the chlorine group on it. And those molecules each have 2 chiral centers, one right here, because that particular carbon has a methyl group. It also has the long carbon chain on it. It has the hydroxy group, and the component that we're not showing is that there has to be, to fill in the tetrahedral carbon, a hydrogen atom there. So we have 2 lines, a wedge, and a dash, which will illustrate to us the 3-dimensional shape of the molecule. So that carbon definitely has 4 different groups bonded to it. Similarly, if we come over to here, this carbon has the chlorine bonded to it, the methyl group, and then the rest of the carbon chain, as well as an unshown hydrogen that would be a wedge pointed toward us. That has to be a chiral carbon as well. So this particular molecule has 2 chiral carbons, as does the one over here. I'll put the 2 stars on it. Those are just carbon atoms that have 4 different groups bonded to it. And so that indicates to us that that molecule will have an enantiomer, a non-superimposable mirror image. And looking at these two particular structures, you'll notice that they both have 2 chiral centers. And regardless of how many chiral centers a particular molecule has, be it 1 chiral center or 1,000 chiral centers, it can only have 1 enantiomer possible. So just like your hands come in pairs, the original hand and its mirror image, so do molecules. So enantiomers always occur only in pairs. You can't have a million different enantiomers of a particular molecule. It will only have the 2 structures. Enantiomers come in pairs, the object and its mirror image. The way you can remember that is like your left hand and right hand. So all chiral centers will have opposite so-called configurations for the 2 molecules to be related as enantiomers. When we talk about configuration, we're going to be using the terminology of R and S to allow us to specify exactly what chirality, what the 3-dimensional orientation is of the chiral centers in the molecule. So we're going to have the terms R and S that we will use to describe the orientation of atoms around each of those starred carbons that we've made at the bottom. Around each chiral carbon, we'll be able to describe the molecule as having the R configuration or the S configuration. That's going to specify the exact stereochemistry of the molecule in words. And we will, in another segment, spend the entire segment going through how do you go about assigning whether a chiral center is an R chiral center or an S chiral center to allow us to specify in words what the 3-dimensional shape of that molecule is at that chiral carbon. And as we mentioned earlier, a molecule can have at most 1 additional enantiomer. So in other words, enantiomers come in pairs. If you have 1 structure and you recognize it has at least 1 chiral center, at most there can be 1 molecule that's related to that as an enantiomer. Enantiomers always come in 2s, in pairs. All right, so that's going to be our enantiomers. Those are the configurational isomers that we recognize as non-superimposable mirror images of one another. And remember that to be a configurational isomer to start with, we have to make sure that we can't just rotate around any carbon-carbon bonds to completely superimpose the atoms of the 2 molecules. And we would find that to be the case down here with these, that no matter how much we rotated around carbon-carbon bonds, we could never superimpose all the atoms. And if you don't believe me, build a molecular model of each of those structures, just like it's shown here on the page with the atoms oriented in front, back, left, right, etc. And you will see that you can't ever superimpose all the atoms without totally breaking the molecules apart and putting them back together some other way. So enantiomers are one type of configurational isomer. The other type of configurational isomer, that is stereoisomers that can't interconvert by rotating around carbon-carbon single bonds, is going to be the diastereomer. And diastereomers are basically everything that's not an enantiomer. So if 2 molecules are not related as those so-called non-superimposable mirror image enantiomers, then they must be instead diastereomers. So we have previously used the terms cis and trans to describe the relationship between our cyclohexane derivatives. And the terms cis and trans, if we use those to describe the relationship between 2 molecules, the cis and trans configurational isomers represent designations of different diastereomers. So, for example, if we look down here, we see this trans configurational isomer. Just as a reminder, it's called trans because this bond points down on the bottom face of the molecule. This bond points up on the top face of the molecule, versus the cis diastereomer, which cis indicates same. So that indicates that both of the bonds, this one comes down on the bottom face of the molecule, this one relative to the carbon comes down on the bottom face of the molecule. So those are oriented in the same face of the molecule, so those groups are cis to one another. So when we describe one molecule as being trans and the other as being cis, that's going to indicate to us that those molecules are related as diastereomers. And remember that no matter how many ring flips we do of a trans molecule, it will never become a cis molecule. No matter how many ring flips we do of a cis molecule, it will never become a trans molecule. So in other words, we can rotate around the carbon-carbon bonds of those rings all day long if we want. We're never going to be able to interconvert between cis and trans. So therefore, those are configurational isomers, and specifically they're diastereomers, because these 2 structures, cis and trans, that we've drawn are definitely not mirror images of one another. Another situation where we run into cis and trans diastereomers is with alkenes. So if we have alkene molecules that have the same connectivity between atoms, meaning the double bonds are in the same place of both molecules, but we notice that there's a difference in how those atoms are oriented around the carbon-carbon double bond, that's going to mean that those are diastereomers of one another. So here we have what we refer to as a trans alkene. We refer to this as a trans alkene because if we look at the carbon atom on the right, the bond going away from the alkene is pointed upward. If we look at the carbon on the left, the bond going away from the alkene is pointed downward. So since those are going in opposite faces, opposite directions from the molecule, from the two carbons there, we describe that as trans. On the other hand, if we look at the structure on the right-hand side, that same carbon-carbon double bond is right here in red. And that carbon-carbon double bond, if we look at the bonds coming from it here and here, what we'll see is that this bond on the right is going upward above the carbon atom. This bond on the left is also going upward above the carbon atom. So we describe those alkene bond as being a cis bond. So these two are described as the cis and trans versions of the alkene, and they are related as diastereomers because we can't rotate around carbon-carbon double bonds. We can only rotate around carbon-carbon single bonds. And so these alkene groups leave the atoms locked into place. And since they are locked into place, due to the carbon-carbon double bond being there and not being able to rotate freely around pi bonds, that means that those two molecules are diastereomers. They are going to be certainly not mirror images of one another, but they are configurational isomers and that they can't interconvert by rotating around single bonds. So therefore, they are diastereomers of one another. As a third example of a diastereomer, we have the two structures shown here. And no matter how much we rotate around carbon-carbon bonds, or no matter how we flip the molecule over, we're still going to always find that we can't make these two structures that we've highlighted in yellow here on the left into mirror images of one another. They're always going to have some atoms in the molecule that will look like mirror images, others that won't look like mirror images, and so therefore they are diastereomers. They're not going to be perfect mirror images of one another. So those two are diastereomers as well. In the upcoming segments, we're going to go in depth about enantiomers, and we're also going to go through some more examples of diastereomers. But the sheet that I'm showing you right now is super duper essential and useful in establishing the relationship between two molecules that we determine are related as isomers. So you should be familiar with going through this flowchart and taking any two molecules and determining what their relationship is, how are they related, by going through each of these step by step by step, starting at the top and working your way down as far as necessary to get to the final relationship.